So can you see the board?
Yes, sir. Yes, sir.
Okay. So in previous class we were fighting with this normalization. Okay. So so the normalization of u1 or ur dagger ur is e by mc square, and similarly vr dagger vr is e by mc square. Okay. Now we have to fix the normalization for psi. Okay. So let us do that. Okay. So integral over space psi r dagger plus psi r plus, we will set to 1. Okay, because this will be total probability density. Okay, and so I will write this psi r plus, okay, as some normalization n e to the power minus I p mu x mu by h cross. Okay, and this u of r, okay, p. Okay, and u of r p come up with this normalization. Okay, uh, so okay, so we have to use basically this. So n square 2e divided by e plus mc square. So let us concentrate on this thing. Okay. Okay, I have set this equal to e by mc square, that fixes n square, but let us not fix at this moment. Okay, so let us see. Okay. So I will keep this n as it is here. Okay, fine. So integral d3x, okay, psi r dagger psi r, that is n square. Okay, this factor will go out. Okay, so you have u r dagger p u r p. Okay, but u r dagger p u r p is d3x n square. Okay, u r dagger p u r p is basically 2e divided by mc square. This I have already counted in that psi. So it is 2e divided by mc square. Okay, so it will be 2e divided by e plus mc square. This is equal to 1. Okay, so now I will integrate over some volume. So this will be n square into 2e divided by e plus mc square v equal to 1. Okay, so n square is equal to e plus mc square divided by 2ev. Okay, so n equal to e plus mc square divided by 2ev square root. Okay, this I can write as mc square divided by ev, okay, and square root of e plus mc square divided by 2mc square. Okay, basically I have multiplied and divided by square root of 2mc square. Okay, and that 2 goes with these 2. Okay, so this psi r plus is equal to square root of mc square divided by ev. Okay, e to the power minus I p mu x mu by h cross. Okay, and this factor, so and this u of r of p, where now u of r of p, I will attach this factor, I will insert this factor in u of r of p. So it will be square root of e plus mc square divided by 2mc square, okay, and that column. Okay, so now you see that this normalization is for u, which is counted now. Okay, then so with this choice, your UR dagger U will be E by mc square. Okay, that E by mc square, if you take psi dagger psi, okay, then that E by mc square cancels with mc square by E, and what remains is 1 over V, and integration over degree x V. So that V cancels with this 1 over V. Okay, that's why this is 1. Okay, clear? Okay, so now the normalization is clear. And we have, so the last point which we discussed in the last class is the equation satisfied by U bar and V bar. Okay. So now from this, one can easily show that from this or by using explicit form of U. Okay. So remember how U bar is defined. U bar of R is defined as U dagger R into gamma 0. Okay. We know what is the normalization for UR dagger. Okay. Now what you can show is that UR bar P UR prime, okay, P is basically delta of RS RP RR prime. So this will survive when R equal to R prime, and when R equal to R prime, this is basically 1. Okay. Similarly, V bar of R P and V of R prime P will be equal to minus delta RR prime. Okay. And so you can show this easily by explicitly computing that matrix multiplication. Okay. And U R P bar V R prime P is equal to 0 equal to V R bar P and U R prime. Okay. So this positive and negative energy solution, the V, the bar of negative energy solution, okay, with, sorry, the bar of negative energy solution with positive energy solution is 0. Okay, so they are also normal basically. This is what it says. Okay. Yeah. Okay. This you can show. Take this as a okay. There are further properties of this spinner. Okay. This 4 component object is called spinner. Okay. 4 spinner. We'll see why this is the case. Okay. So there are further important properties of this U's and V's, but we will require the transformation property of psi for that to establish those properties. It will be easier. Okay. But that we'll discuss after when we discuss the transformation property of psi under Lorentz transformation. Okay. And so now we know the plane wave solution for free Dirac equation. Okay. Good. So any doubt so far? Now let us move on to next topic, is Dirac equation coupled electromagnetic field. Okay. So I will just recapitulate what we need to do. Okay. So in the presence of electromagnetic field, your P mu must be replaced, P mu, which is I H cross del mu. Okay. This should be replaced by P mu minus E by C A mu. Okay. This implies that del mu must be replaced by del mu IE by CH cross. Okay. A mu. So this replacement in free Dirac equation will give us the Dirac equation in the presence of electromagnetic field. Okay. So let us do that. So let us first write the Dirac equation in the Hamiltonian form. So IH cross. Okay, so let me write in the covariant form and then I will go to Hamiltonian form. Okay. So in the covariant form, the Dirac equation is IH cross gamma mu del mu, okay, minus MC acting on psi equal to 0. So this is a free Dirac equation. Now what we need to do, we have to substitute, we have to replace it with these factors. Okay. So it will be IH cross gamma mu del mu, these remain as it is, plus IE by CH cross, and there is a IH cross, so it will be minus E by C gamma mu A mu, okay, minus MC psi equal to 0. Okay. Right. So you can now write in the Hamiltonian. Okay. So it will be IH cross, okay, gamma 0. So now I will multiply by gamma 0 from the left. Okay, so I will get gamma, first term in this expansion will be gamma 0 del 0. So gamma 0, and when I multiply from the left by gamma 0, I will get gamma 0 square, which is identity. Okay, so I will get IH cross del psi by del t. There will be C here because it is a del 0. So C I will multiply throughout. Okay, so IH cross del psi by del t equal to minus minus IH cross C. Okay, there is a special part. Okay, del mu is minus IH cross P mu. Okay, okay. So this I will write as minus IH cross gamma 0 gamma I is alpha I. Okay, so it will be alpha dot gradient. Okay, plus I am taking this to right hand side. Okay, so there will be plus E by C. Okay, A0. Okay, because I have multiplied by gamma 0 from the left, so this will be A0. There is an identity here which I am not writing. Okay, minus E alpha dot A plus MC square, okay, gamma 0, that is beta, acting on psi. Is this clear? Okay, I've done nothing. I just expanded this. It will be gamma 0 del 0 plus gamma I del I. IH cross del I, when I bring it to right hand side, it will be minus IH cross del I. Gamma I del I, okay, is gamma dot gradient but there is a gamma 0 which is multiplying from the left. So gamma 0 gamma I vector gamma I vector gamma. So alpha dot is gradient. Okay. So this entire bracket is acting on psi. Okay. So this I can write it in a better form. Okay. So this I will write as IH cross d psi del psi by del t equal to minus IH cross times this gradient is momentum operator. So it will be C alpha dot momentum operator. Okay. But then there is this alpha dot A is also there. So when I take alpha common, so I will get vector P operator minus E by C A. Okay. Here plus there is C. Why there is a C here? There should not be C. Okay. So E by C, when I multiply by C, this C should go. Okay. So there is no C here. So it is E phi. This is a scalar potential. A0 is this capital phi times identity, okay, plus mc square beta, and this entire term will act on psi. Okay, so this is your Hamiltonian for the Dirac equation in the presence of electromagnetic field. It is expected. This momentum is replaced by momentum minus E by C vector potential. Okay. So now what I will do, okay, I will assume the solutions of this form. Psi of Px, okay. So I will assume that phi, the scalar potential, and the vector potential are time independent. Okay. So I can use the stationary state answer. Okay. What is your stationary state answer? Psi of Px is equal to two components spinor, phi and chi, e to the power minus I e t by h cross. Okay. This momentum factor, I cannot write here e to the power, I cannot write this as e to the power minus I p mu x mu by h cross because it's not a free Dirac equation. So that x part will be hidden somewhere here in phi and chi. Okay, that I don't know because it's not a free Dirac equation. I can just assume this. I can assume minus or plus here. Okay, but you will see there is no need of putting plus here. This will be already counted as negative energy solution. Okay, so let us concentrate on this positive energy solution. Okay, so this is my psi. Okay, I repeat. Okay, this x dependent part in the free plane wave solution, what we had p mu x mu, okay, by h cross. So it is e to the power minus I e t by h cross and e to the power plus I vector p dot vector x by h cross. That I cannot do here because it's not a free Dirac equation. So that x dependent part will be here, hidden somewhere here. Okay. So I cannot directly assume phi and chi to be 1001. Now I will substitute this and such in this. Okay. So if I do that, okay, what I'm going to get? IH cross del psi by del t will be, if I add del t on this, I will get minus I by h cross. So h cross will cancel, I will cancel. So it will be E times energy times phi and chi, okay, and e to the power minus I e t by h cross. Okay. Similarly, C times alpha dot P minus E by C A. Okay, acting on psi. Okay, so this will be equal to C. Okay. What is alpha? Alpha is 0, sigma, sigma, 0. Okay. So it will be, I will get 2 cross 2 0, then sigma dot P minus E by C A. Okay, then I will get sigma dot P minus E by C A. Okay, and then I will get 0. And I have to act it on psi. So psi will be these two components spinor, phi and chi, and e to the power minus I et by h cross factor will be there. That I am not writing. Okay. So when I substitute this in this expression, okay, what I am going to get? Okay, I will get the following. I will get so I will first write this matrix 0 sigma dot P minus E by C A. Okay. Sigma dot P minus E by C A 0 acting on phi chi is equal to, okay, see, this term I have written acting on this phi chi, okay, this is equal to this minus this piece. Okay, so that I can write in the following. So del del T is E times this two components spinor. Okay. So this will be E minus E phi, okay, times identity. Okay, there is an identity here also, minus MC square beta. Divided by C, because there was C here. Okay, so it will be divided by C acting on phi chi. E to the power minus IT by h cross, e to the power minus IT by h cross cancels. Okay, fine. So let us write now. This is the equation for 4 components spinor. So you can now matrix multiply and you can write this as sigma dot P minus E by C A acting on chi equal to, okay, this is identity, okay, this is identity. So upper upper block in beta will be identity and lower block in beta, lower diagonal block in beta will be minus identity. Okay, so for chi I will get E minus E phi, okay, minus MC square, this identity into phi divided by C. Okay, so this is equal to this. And for other component I will get sigma dot P minus E by C A phi will be equal to, now I will get plus sign here because beta has this lower component of beta is minus 1. So this is minus identity, 0, 0. This is your beta. Okay. So I will get E minus E phi, okay, plus MC square divided by C equal acting on chi. There is identity here. Fine. So you from this you can easily derive the expression for phi. Now what you will do, okay, you write this for chi and substitute here. Okay, so what I am going to get, okay, so chi will be c times sigma dot p minus e by c a divided by this factor. Okay, and I will substitute here. Then I will take this c here, so I will get c square sigma dot p minus e by c a. Okay, it's square, okay, divided by e minus e phi plus mc square, okay, equal to e minus e phi minus mc square phi. This will act on phi. Is it okay? No problem. So I just substituted, I evaluated chi in terms of phi and substituted here. So I have the equation in phi now. But now you see, you concentrate on this expression. Okay. We want to see what happens. Okay. So this is the equation without any approximation. There is no approximation at all, except the fact that the phi scalar potential and the vector potentials are time independent. Apart from that, there is no other assumption. Okay. But now you see, what is your E? E is mc square, okay, plus E non-relativistic, right? Okay, this is your total energy. So we now concentrate on the non-relativistic limit. Okay, so in the non-relativistic limit, okay, we assume that this energy, non-relativistic energy, is much less than mc square. Okay, so this factor is much less than this. That means E is approximately equal to mc square, and the scalar potential, okay, so basically this will behave as, okay, E, if I write E as mc square plus ENR minus E times scalar potential is basically your kinetic energy. So we will assume that E times phi is also less than mc square. E phi, but E can be, this can be negative. So I will take, this is mc square. So this is my non-relativistic approximation. Okay. So ENR is much less than mc square. So total energy is only rest energy. Okay. So now let us concentrate on this factor. Okay. C square divided by E minus E phi plus mc square. Let us concentrate on that. Okay. C square divided by E minus E phi plus mc square. E minus E phi plus mc square. Okay. This I can write as 1 over 2m. Okay. Then I will write here as 2m c square. Okay. And this will be, this I can take, okay, what I will do, I will write this E as mc square plus ENR. Okay, that mc square will add with this mc square, so it will be twice mc square here and ENR. Okay, so I will get ENR plus 2mc square minus E phi. But this is equal to 1 over 2m. 1 over 2m. Okay. This 2mc square I can divide, so I will get this as 1 over 1 plus ENR minus E5, okay, divided by 2 mc square. And in the non-relativistic limit, this is much smaller than this. So now I can expand this denominator. Okay, this entire thing I can expand. Okay, so what is that expansion? 1 over 2m. Okay, what is the first term in the expansion? You do the power series expansion. Okay, so it will be 1, okay, plus here, so it will be minus ENR minus E5 divided by 2 mc square. Okay, plus ENR minus E5 divided by 2 mc square, its square, and so on, minus dot. Okay, still there is no assumption. When I truncate now this series, that means I am implementing this approximation. So it's not assumption, approximation. So up till now, this is exact. I have not done. This is a series, infinite series. Okay, clear? So this is the expansion in ENR minus E5 divided by 2 mc square. In the non-relativistic limit, so suppose I want the 0th order part. Okay, so what happens to 0th order? 0th order in ENR minus mc square divided by 2 mc square. Okay, what happens in 0th order in this? Okay? That means I need to consider only this term. Okay, but we have to be careful. This is not the only thing. Okay? We have this part also. But you see, here I cannot neglect anything because this is E minus mc square. So when I write E as ENR plus mc square, this mc square and mc square term cancels. Okay, so ENR minus E5 remains. That I cannot neglect. Okay, it's not, there is no comparative in this expression. Okay, so this is basically ENR minus E5. This I have to keep. I cannot neglect this. Okay, so at 0th order, what I'm going to get? At 0th order, at 0th order, I will get 1 over 2m sigma dot P minus E by CA square. Okay, this is the operator part acting on phi equal to so at 0th order I will collect only this term. So this will be 1. I have already written 2m here, so there is no. So I'm taking basically this series on the right hand side. Okay, here. So let me write first the entire expression and then I will write the 0th order term. Okay. So 1 minus ENR minus E5 divided by 2 mc square plus ENR minus E5 divided by 2 mc square minus dot into ENR minus E5. Okay, acting on phi. Okay, this factor is coming from this. Okay, so now at 0th order, order in E nr minus E phi divided by 2mc square, what I'm going to get? 1 over 2m sigma dot P minus E by CA square phi, remember pi is a two components planar, is equal to 0th order. So keep only this term. So it will be E nr minus E phi acting on phi. Okay. Therefore, this is nothing but 1 over 2m. This is 1 over 2m sigma dot P minus E by CA, okay, square plus E phi. Okay, this I have written on the left hand side, acting on phi equal to E nr phi. So this is like your Schrodinger equation. H acting on phi equal to E nr phi. But this is two components planar. So it's not actually the Schrodinger equation, it is the modified version of it. It's called Pauli-Schrodinger equation. Okay? I will explain later on what is this Pauli-Schrodinger equation. Okay? So in the non-relativistic limit, we have this equation. And let us now concentrate on this piece. Okay, let us now concentrate on this. Okay, let me explain this. What is Pauli-Schrodinger equation? Okay. Because otherwise you will not understand the non-relativistic Pauli-Schrodinger equation. Okay, so let us consider a free particle. Okay, for a free particle, what is your Hamiltonian? Usual quantum mechanics. Okay, it is p square divided by 2m. Okay, now suppose what Pauli did is the following. Suppose I want to say this is the Hamiltonian for free particle which has some spin, which has half integer spin. Okay, which is put by hand in the Hamiltonian. How to modify this Hamiltonian so that the spin information is also there? How I can modify? To modify it, we must note that even if you put spin, okay, the Hamiltonian form should be of this p square by 2m, but the spin information should be there. Okay, p does not carry any spin information. Okay, this is your linear momentum. Okay, instead of that, suppose if I consider the following: h equal to sigma dot p, its square, okay, divided by 2m. Okay, if I consider suppose this Hamiltonian, where sigma is your usual Pauli spin matrix, what is going to happen? Okay, sigma dot p is sigma dot p into sigma dot p. So I'm just writing this part, this numerator. Okay, there is 1 or 2m is there, but I will now concentrate on this piece. Okay, so sigma dot p times sigma dot p is what? Sigma I pi sigma j pj. Some more I, some more j. Okay, this is equal to sigma I sigma j pi pj. Okay, because this is 2 cross 2 matrix, but momentum is in different space, so I can take this pi through sigma j. There is no problem at all. This I can write as sigma I sigma j pi 2 times sigma I sigma j pi pj plus pj pi divided by 2. Okay, I have done nothing. Okay, just divide by 2, multiply by 2, and pi pj is written like this. No, this should not be 2 because I have written 2 terms. Okay, so there should not be any 2. Okay, fine. Or maybe, okay, I will write in a more simple form. So this I can write as sigma I, sigma j, noting that pi pj is symmetric in ij. Sigma j, sigma I divided by 2 pi pj. Okay, so I wrote previously in completely in reverse way. Okay, so this is the correct way of it. Okay, so I use the symmetric property of pi pj. But what is sigma I, sigma j plus sigma j, sigma I is anti-commutator of sigma I, sigma j divided by 2 pi pj. What is anti-commutator of sigma I, sigma j? Is twice delta I, pi pj, and divide by 2. So these two will cancel. Delta ij pi pj is just p square. Okay, so this term is basically p square. So this Hamiltonian is same as this Hamiltonian, written in different form. Okay, clear? So this is Pauli's Hamiltonian for free spin half particle. Now if I consider the free spin half particle interacting with electromagnetic field, all I need to do is replace P by P minus E by phi, E by C phi, E by C A. And if there is a scalar potential, then I have to add E times scalar potential term. Okay? Yeah? That is nothing but this. Okay? So the non-relativistic limit of Dirac equation in the presence of electromagnetic field is Schrodinger-Pauli equation. Is this clear? So we are on the right track. So the non-relativistic limit of Dirac equation produces the known result. Okay, in your usual non-relativistic quantum mechanics. But let us investigate this term further. Okay. Now the non-relativistic limit, I can write this as the following. I will write this so now we have to do some algebra with this sigma matrices. Okay. So let us open this bracket. Let us now open the bracket. Sigma dot P minus E by C A, its square, is equal to sigma I Pi minus E by C A, then there it will be AI, and note that this is acting on phi. Sigma I Pi minus C AI, then sigma J Pj minus E by C Aj, summation or I, summation or J, acting on phi. Okay, let us see what it gives. Okay, what is the first term? Sigma I Pi, sigma J Pj. Okay, so it will be sigma I Pi, sigma J Pj, that I will write as sigma I, sigma J Pi Pj, which is same as this term. Okay. minus E by C sigma I pi, but remember this P is now operator. This P is operator here. Sigma I pi acting on this AJ, and so this pi is acting on AJ and phi. Okay, so this is sigma E by C sigma I pi AJ. Okay, and this we should note that this pi will act on AJ, so it's like this. Okay, fine. I will keep this uncompleted bracket. Okay, then this term with this. Okay, so it will be minus E by C. Okay, sigma I sigma J. Okay, AI PJ. Okay, this term, and then last term minus this, it will be plus E by C square by C square. Okay, sigma I sigma J AI AJ, and this entire thing will act on phi. Okay, this term is P square. Okay, so this term is P square. Operator P square. Okay, what is this term? Okay, minus E by C sigma I sigma J. Okay, plus E square by C square sigma I sigma J. Okay, I can write these two terms as the following. Okay, okay, so let me use the following property of sigma matrix. I hope you know this. Sigma I sigma J equal to delta Ij. I can use the following property. Sigma I sigma J equal to identity times delta Ij, okay, plus I times epsilon I j k sigma k. Okay, you know this property. I asked you to come prepare with this properties of sigma matrix. This is one of them. Okay, so basically you can use it here. Okay, you will directly get P square. Okay, because this is symmetric in Ij, this is anti-symmetric in Ij. This term multiplying with this term will cancel, will give me 0. So only delta Ij term will contribute. Okay, so if I use that, sigma I sigma j pi pj is basically P square. Now let us concentrate on this. What is this? Sigma I sigma j ai pj. Okay, so this is delta ij ai pj. Okay, so this term is basically, I am writing this term, so it will be sigma I sigma j ai pj is equal to identity times delta ij ai pj. Okay, so this is like a dot p. Okay, plus I times epsilon I j k sigma k, okay, ai p. Keep this as it is. Then this term, okay, this term is sigma I sigma j ai aj. This is nothing but just a square. Okay, for same reason. Okay, now if you collect this term, if you collect this term and if you collect this term, okay, what is going to happen? Okay, there is one more piece which I am missing. Okay, this term is actually wrong. Actually, this sigma I, sigma j. This sigma j is missing. Okay. Now let us concentrate on this piece. Hmm? Sigma I, sigma j, pi. Hmm? So first one term will be pi aj acting on phi, and another term will be aj pi acting on phi. Okay, so I'm considering a term which is pi aj. Okay, so it's like pi aj. Okay, this times phi. Okay, what does it mean? If you write p in as a derivative operator, so it will be del I aj acting on phi. This is what it means. So let me do it carefully because it's chance of confusion. Okay, so pi aj, okay, and this will act on phi. Okay, this is equal to sigma I, sigma j, okay, minus I h cross, okay, del I, correct, acting on aj phi. Now the bracket is complete. Okay, this is equal to minus I h cross sigma I, sigma j, del I aj, okay, times phi minus I h cross sigma I, sigma j, okay, aj pi. So here is del I phi. Okay. So I will now collect this term, this term, this term, and this term. Okay. What is it? I can simplify this term further. Okay. I can simplify this term further. So let us do that. So let me write that. This sigma I, sigma j, ai, pj, okay, plus sigma I, sigma j, aj, pi. So AIP. Okay. So let me write, let me consider this term, okay, and consider this term. Okay, and let us write. Okay. So del. Okay. So this I have already. Just a minute. This is A dot P. Yeah. This. Fine. This term is okay. Okay. So let us not correct this term. Let us consider this term. Let us consider this term. Yeah. So let me okay, fine. Let me consider this term total, okay, and let us consider this term total, okay, total. Let us see how it, what we get. Okay. So sigma I, sigma j, ai pj, ai pj, okay, plus plus sigma I, sigma j, sigma I, sigma j, which is there. Just a minute. I want to collect this term. Okay, fine. Okay, so let us consider this term that we have already taken. Okay, then sigma I, sigma j, pi acting on aj phi. Okay, so this will act on phi. Okay, this will sigma I, sigma j, pi aj acting on phi. Okay. We have already simplified this term. So now you can use these expressions. Okay, so it will be a dot p acting on phi, that is this piece, plus I epsilon I j k sigma k, okay, ai pj acting on phi, okay, plus this term. Okay, this term is sigma I, sigma j. So that is sigma I, sigma j. If I use this delta j and epsilon ijk, etc. Okay, so this will become minus. So let us do that. Okay, so it will be minus I h cross delta ij delta ij del I aj acting on phi, del I aj acting on phi. Okay, then minus I h cross. So there will be another term which is here, it will be minus I h cross I times epsilon I j k, okay, sigma k, okay, del I aj acting on phi. Okay, that is this term. Okay, now this term. Okay, so plus into bracket minus I h cross delta aj aj del I aj del I acting on phi. Okay, minus I h cross. Okay, then there will be I, okay, epsilon I j k, okay, sigma k aj del I acting on phi. Okay, so now it's complete. Good. This term remain as a dot a dot p remain as it is. Okay, now you concentrate on, okay, this piece. Okay, this piece gives you delta aj del I aj. It's like del dot a, divergence of a. Okay, clear? This piece, so you concentrate on this piece, epsilon I j k sigma k ai pj and epsilon I j k, okay, sigma k. Yeah, so this piece is also not required. Yeah, this piece and this piece. So let me. So you collect this piece and this piece. Okay. This becomes. So let me write it. Okay, plus it will be minus I h cross You tell me if your time is up. Okay. Del dot A 5. Okay.
Hello.
Hello.
So, Sudipto sir has already started his meeting.
Okay. So, okay, I will finish this term and then I will stop. Okay. So this is
Okay.
del dot
Yes.
A. Okay. This is epsilon ij k del sigma k del I aj. Okay. This term I will collect with this term. Okay. Fine. So there will be a contribution from I times epsilon ij k sigma k del I aj acting on phi minus IH cross delta Ij. So this will be A dot P term, okay, acting on phi. Okay, and this term with this term we'll see what will be the contribution. Okay, so we'll continue with this tomorrow. Okay, there is some interesting result which will come out from this. So I'll repeat some few steps and we'll finish this exercise tomorrow. Okay. So I'll stop this and I will message you the timing for tomorrow's class. Now you can join maybe.